So in the last lecture we discussed about how the aerodynamic admittance function can be used to simplify the randomness involved in computing the wind loads on marine structures. For more information on this specific function you can refer to this particular paper. So this book will give you more information on the computation and the influence of aerodynamic admittance function in the wind loads. So we already saw in the last lecture that how the mean component and the gust component are handled in the wind load calculation, provided we have the spectra defined for mean wind depending upon the 1/7 power law. There are other spectrum available for average wind speed which can be used for offshore application, which we will see in this lecture. Now the wind spectra which will be given now will be actually a function of circular frequency, which is quite unusual. But the following conversion can be used. To understand these spectra. So yeah, u plus omega will be actually a function of which I say g u plus f. That is the conversion what we have to convert the frequency to circular frequency when you have otherwise the frequency given in general. So there are many spectra available. Let us talk about few of them which are used for offshore application. Davenport has given a spectrum. There is another spectrum suggested by Harris, which is also used for marine structures. in both the spectrums the dimensionless value theta is given by the following relationship. So, this can be also 2 pi by omega is f, we already know, for any value now in this case L10 LU is called integral length scale which is taken as 1200 for Davenport and 1800 for Harris. Delta is called surface drag coefficient which is dependent on u bar. Now that value 10 here is what is called reference height, 10 meters above the mean sea level. This is where you generally compute the wind velocity, that is called reference height. So, the value of delta is generally taken as 0.001 for offshore locations. So, these two spectrums are also popular to compute the wind forces on offshore structures. Now, there are some critical comments about these two spectrum. It is very interesting to note, it is very important to note that both the spectrums are not derived for wind speed analysis offshore. They are done or they are computed based on wind speed average observed onshore. So, there has been a very serious problem of using the spectrum for offshore. People have been questioning the spectrum. Now, one may wonder that what would be the significance of using a wrong spectrum which is not meant for an offshore location. Now, as far as the bottom supported structures are concerned, we have already discussed this in the last lecture. We can classify the marine structures into two divisions. One is what we call fixed structures, you may say them as stiff structures, I can call them as bottom supported structures. Examples can be gravity based platform, jacket platform, etc. The other could be flexible, more compliant structures. Examples could be TLP, articulated towers, spar, triceratop, etc. We have already seen in the last lecture, if you recollect, as far as forces acting on marine structures are concentrated, the fixed type structures will be more prone to earthquake forces, whereas the compliant type structures will be more prone to what we call wind induced vibration. That is one part of the argument. Now, carrying this argument forward for modern application of marine structures. Now, the essential function of a marine structure as on today, one of the major requirement of a marine structure could be, let us say, oil and gas exploration. The moment we agree that oil and gas exploration is one of the main functional aspect of any marine structure as on the present requirement, then we are looking for oil and gas exploration in ultra deep waters or at least deep waters. The moment I say the water depth is increased, I cannot go or I cannot afford to go for fixed platforms because they are completely obsolete. People go for what we call new generation offshore structures. Essentially, these kind of new generation offshore structures are compliant and they are generally taut moored systems. It means they are supported by tension in teethers. Having understood that the current purpose of marine structures are oil and gas exploration in ultra deep waters, where new generation structural form is evidently improving or it is important. Therefore, wind forces or wind loads acting on these structures which can cause wind induced vibration becomes dominant apart from the wave load. Now, when the wind induced for vibration or the wind loads become dominant in such structures because of low frequency phenomena, it is important that we must select an appropriate spectrum for defining my wind loads. So, in the present trade, people have replaced Davenport and Harris spectrum by specific spectrums which are very applicable for flexible, taut moored, compliant offshore structures. So, what are those spectrums? So, specific recommended spectrum for, I should say here, compliant structures, essentially they meant for flexible structures which have low frequency range. What do you understand by low frequency range? The fundamental time period of compliant structures vary somewhere from 75 seconds to as high as 125 seconds. So, we all know frequency is 2 pi by T. So, when the T is higher, frequency is lower, and we also know that wind is a low frequency phenomenon. Okay. We have already seen this in the last lecture. Now, here I have a structure which has got a fundamental frequency very low. I also have a load which is having a low frequency phenomena. So, there is a possibility that the structure may resonate under this combination of action of the wind loads on these kind of structural action. So, looking into this consideration, people have specifically recommended 3 spectrum for wind loads on compliant structures. One is Kaimal spectrum, the reference of the spectrum can be seen from Dyrby and Hansen 1997, which I gave you in the same lecture today. So, according to this spectrum, I should say this is equation number 5. So, theta in my case is as same as the dimensions value as specified in the Davenport and Harris spectrum, which is omega Lu two pi u bar. Since the Lu value is associated with a specific dimension related to Davenport and Harris, the improved version of Kaimal spectrum says theta simply is replaced as ratio of omega by omega p, where omega p is the peak frequency. And of course, sigma u square is the variance I will write it here. Sigma u square is the variance of u of t at reference height of 10 meters. Subsequently, API 2000 also specified a spectrum which is very much applicable for compliant structures. I call this as API 2000 spectrum. Equation number 6. Now, one may wonder what is the variation between the Kaimal spectrum and API spectrum. The major variation comes from the sigma u, which is made now as a function of z, okay. Whereas in Kaimal spectrum this was always taken at the reference level of 10 meters. Now, this is the function of depth also, or I should say height. So, I should say that this is not independent of Z. That is the catch in API spectrum. So, they have given a range 0.01 is the value what you can select for the specific application of the spectrum. Usually a value of 0.025 is chosen. Then in that case the standard deviation of the wind speed is given by that is sigma u of z, which is a function of z, 0.15 of whereas in this case Zs is thickness of the surface layer, usually taken as meters. So, I can call this as equation number 8. So, if you know the thickness of the surface layer, which can be considered as 20 meters, you can always find out what z you want to compute your standard deviation, pick up the equation, square that, you get the spectrum defined, because you already know omega p. For every value of omega you will get s plus omega from this equation, which AP specifically applies or advises for complaint structures. Let us quickly see what is the plot variation of Davenport, Harris and for example API, and see in which range this particular spectrum is more effective. So, I am trying to plot the variation of theta with the spectral ordinate for these 3 spectrum, for Davenport, Harris and API, for which we already have the equations. This is the Harris spectrum. This is Davenport. This is AP. So, we draw very important information from these figures. The important information what I get by comparing these 3 spectrum is that for lower values of theta, when the value of theta will be lower, because LU, U10, 2 pi are all fixed. When omega is lower, theta will be lower. It is true in case of API also, because omega p is fixed. For omega to be lower, theta will become lower. It means for lower frequency range, the variation between the spectrums are significant. So, at lower frequencies, the variation are significant. On the other hand, Davenport and Harris underestimates the wind load on marine structures at lower frequencies. The variation is very significant. Okay. Now, one may ask a question that why we are interested in lower frequencies, because structures which has lower frequency range are prone to wind induced vibrations. So, we are very much focused on the lower frequency ranges. For example, in case of let us say TLP, in case of spar, in case of triceratop, in case of MLATs, that is multi-leg articulated towers, the fundamental frequencies are of very low order. So, these structures are also taut moved, or I should say simply moved. Therefore, the effect of wind induced vibration on such structures are dominant. So, it is necessary that I must compute the wind loads on these structures which has lower frequency band in an appropriate manner, because if you compare the classical spectrum available in the literature at lower frequency bands, the variations of the spectral ordinate given by the spectrum are significantly different. Okay. So that is why people use APA 2000 for flexible structures, and Davenport and Harris also had a very serious constraint that they were not validated depending upon the wind speed average measurements done on offshore, they are all done on measurements based on onshore. So there is a difference. So the question is whether they can be applied to offshore is an issue. This is about wind spectrums. Okay, is this clear? So this will be the discussion what we will winding up for the wind forces on marine structures. We have discussed aerodynamic loading, we have now discussed aerodynamic loading. We have understood that the aerodynamic loading are two components. One is what we call the mean wind speed or the mean component of the wind velocity, the second one is the gust component, which is the variable component which can cause dynamic effects on the structures. The static component, which is the mean wind velocity, will not cause dynamic effect, it is going to cause static effect. So generally courts prefer to do quasi static analysis, but it is very important that structures with low frequency range should be accounted for the dynamic amplifications happening because of the gust factor coming from the wind load on low frequency structures, which cause, because this can cause wind induced vibrations. Therefore it becomes necessary that I must know how to handle the gust factor also into my account. Now the question is, as far as earthquake loads are concerned, though it is a random process, we can do deterministic analysis, but as far as wind loads are concerned, people generally do probabilistic analysis. Therefore I want to convert or handle this probabilistic analysis into a confined closed form in wind load computation. So I use or introduce what we call aerodynamic admittance function into my calculation. So with the help of that function I can always compute the wind loads, which will also account for the gust factor in my problems. Okay, and we already started comparing wind, wave and earthquakes. Earthquakes create inertia forces, they never create a drag force on the structure. They are highly sensitive to structures which are bottom supported and large, of course, massive structures, whereas wind has a drag component also, wave has a drag component, inertia component both. So we have now completed two discussions, one on hydrodynamic or the wave loading. We started with Airy's theory, we understood there are higher order theories available like Stokes fifth order, etc. They are available in the literature, this course will not cover those aspects in detail. We also discussed about how to handle the nonlinear drag part. We have also discussed how to handle the damping part and what is the approximate value suggested by the literature for flexible or for bottom supported cylindrical structures or structures having cylindrical members. Then we moved on to aerodynamic loading. We started with understanding the aerodynamic behavior on different class of structures. Aerodynamic aspect is divided in two parts. One, the way in which you model the loading itself is a problem. Two, where do you want to apply this load, to a fixed structure or to a flexible structure, it is a problem or it is varying. So we must specify very clearly what spectrum I must apply for different kinds, because certain spectrums show significant variations in the low frequency bands and those are the structures which are highly aerodynamic sensitive. Okay. So we have understood this. Now we will talk about additional loads, like for example ice loads, then we will move on to earthquake loads, then we will move on to conventional dead loads, live loads, current forces, etc. So that will comprehensively complete